My friends, let's take a look. For warm-up one, I think most of us just, in a way, kind of t-table it in our heads, or you've done it so many times that you kind of have the pattern memorized and you don't even think about the t-table anymore. Either way, you know, it works. So if y equals x squared, I hope it makes sense. If x is 0, y is 0. So that gives you the vertex at the origin. Since we're squaring, it doesn't matter if you square positive or negative 1. You're going to get positive 1 out. So from the vertex, the pattern is basically, you know, out 1, up 1. And then it doesn't matter, again, if you're putting positive or negative 2 in, you're going to get 4 out in this case. And so from the vertex, the pattern would go out 2, up 4. There we go. And I hope this is something that we don't really need to do the t-table for anymore. But at the same time, I hope that if you ever get stuck, you know that the t-table, of course, is there for us. So there we go. All right. Whew. Okay. Me using this Del pen is not always the most beautiful thing you've ever seen. A note, since we're going to be graphing quite, enough parabolas to, try to be good at it, do know that no one should ever poke their eye out with a parabola. So try to make it rounded here toward around the vertex as opposed to pointing, kind of trying to show off that this is a parabola. You don't think it's an absolute value function or, something that you could poke your eye out with. All right, now let's move on to x equals y squared. For this one, I would maybe, still think about a t-table. Just this time your input is y instead of x. So instead of putting 0 in for x, put it in for y, and see what you get out. You still get 0, 0. And in this case, if you put positive or negative 1 in for y, it won't matter. You're going to square it anyway. So you get positive 1 out. So that would turn into the 0.1, 1, and then the 0.1, negative 1. Hopefully that makes sense. And then if you plug in plus or minus 2 in for y, then you'd get positive 4 out for x. And so, so you could, from the vertex, go up 2 to the right 4, or from the vertex, go down 2 to the right 4. And there you go. So basically, the point is this. You're expected to be able to graph y equals x squared with 5 points of accuracy as a parent function, and then also to be able to graph x equals y squared with 5 points of accuracy as if it's a parent function, and the pattern is exactly the same. It's just if it's y equals x squared, your pattern, your head could be in a way like in normal position. And then if it's x equals y squared, you can almost like turn your head, to the side, right? Like rotate your head 90 degrees to the right. And then act like you're graphing y equals x squared because it's the same pattern, just opening to the right instead. So there you go. And then language, some people might think it's strange that I call x equals y squared a function since it quite obviously fails the vertical line test. But we would say x equals y squared is a function of y. Because it passes the vertical line test, or sorry, excuse me, it passes the horizontal line test. There we go. Okay. Anyway, so you have a new parent function, basically. Okay, now let's look at warm-up 2 here. I'm hoping that you can remember how to complete the score, and if you have forgotten, then hopefully you can, brush up and pick it up again, okay? And how come? Well, because we are going to complete the square many, many, many times in Chapter 9. As a matter of fact, pretty soon we'll have problems where we have to complete the square twice within the same problem in order to complete it. So let's make sure that you remember how to do it, shall we? Okay, so I'm going to combine steps 1 and 2. Step 1 is to group the x terms, and step 2 is to factor out the leading coefficient. Whether it's a common factor or not, you factor the whole thing out. Okay, so in this case, this is what it would look like. 2 times x squared would give you that front term, and 2 times negative 6x would give you the second term. Okay, next, kick the constant term out. I know that there are other methods that you may have learned in the past for completing the square where you leave the constant term or part of the constant term in. It's not going to work very well. Truth be told, it never did work very well. Anyway, so it's time to switch over to this method as of Chapter 9. Okay, next, to find out this magic ingredient that goes right here, you're going to take your linear coefficient which is -6, you are going to divide it by 2, you'd get -3, and then you're going to square the result, you'd get +9. Now, be careful. We just added, it looks like I added 9, but I actually added 2 times 9. So I'd have to subtract 2 times 9 back off on the outside. And so that step is known as adding a fancy version of 0. Okay. And so, adding 0 wouldn't change the value. In this case, it just changes the appearance. So it's just a little cosmetic change. And why did we do that whole divide by 2 and square the result? Well, it's so that we could have a perfect square in there. And that's why the process is known as completing the square. So x minus 3 quantity squared would expand out to be x squared minus 6x plus 9. And then you just combine like terms there with the y terms. So you'd have minus 5. I'm going to bring f of x down like that. All right, my friends. So let's go ahead and graph this, and we're going to talk about having you think about this exact thing just a little bit differently. Okay, so let's see. Horizontal shifting rules. So subtracting 3 on the inside shifts your graph to the right 3. Subtracting 5 on the inside shifts your graph down 5. And so vertex would not be at 0, 0. It would be to the right 3, down 5. And then from there, you have this stretch factor of 2. So we're going to do an x squared pattern, but we're going to double your heights. And so instead of going from the vertex out 1, up 1, we're going to go out 1, up 2. Because you'd have to double your results there. And then instead of going out 2, up 4, you're going to go out 2, up 8. Which I think puts you here. Yeah. And then to the left 2 from the vertex, up 8. And then fill it in. Doing your best. Oops, doing your best to make it, look symmetric and not be something that anyone could poke their eye out with and all that stuff. There we go. Sometimes these, the really vertically stretched parabolas, it's hard to not make them look pointy at the vertex, but do your best. There we go. Okay. All right, my friends, I hope that I hope this is helpful to you. I do want to point something out before we move forward. This is going to get a little more interesting soon. And so, I want to have you guys think about your shifting rules a little differently so that we can get a little more mileage out of them and make all of Chapter 9 a little bit easier. So first thing I'm going to do is rewrite this vertex form. And I'm just going to replace f of x with y. No big deal because f of x is y, right? And then the next thing I'm going to do is, and this is going to seem weird right now, but then pretty soon it'll make sense as to why I'm having you switch the way you think a little bit. I'm going to add 5 to both sides of the equation. And so I'd have y plus 5 equals 2 times x minus 3 squared, like this. And what I want you to know is that for Chapter 9, this is what we will refer to as standard form for a parabola. And I want to talk with you about how to interpret it. And it shouldn't undo what you've learned in the past. It should really just kind of validate what you've learned in the past, okay? So you know how in the past we've been told if you are subtracting a number from x, or let's say if you're adding a negative or whatever you want to say there, I'm just going to say if you're subtracting a number from x inside a function, then it would shift your graph horizontally to the right 3. So in a way, when you see addition or subtraction on the inside of a function, it's sort of counterintuitive. Like when I see -3, I think left, right? But it's kind of a game of opposites. So if you see -3, you go to the right. Okay, well, in a way, that y plus 5, since I moved the 5 over, you can see that we're adding 5 in a way inside a function. So the function would be, basically y to the first power. And so you're adding 5, you're adding it to y. Y is a vertical movement. So simply because you're adding it to y, you can tell it's either up or down. It's a vertical movement. And then similarly to the rule you learned over here with horizontal shifting rules, if you're adding inside a function, instead of going up 5, you'd go down 5. So it's kind of a game of opposites here as well. In a way, it's a little more consistent with, the horizontal rule there. So this would be a matter of going down 5. So what I'm trying to do here is just give you a different way to get to the same answer. If you write it in this standard form right here, you'd still shift it to the right 3. You'd still shift it down 5. You just have a different way to write it before you make that determination. Okay. And at this point, when we're doing a simple one like this, it's not especially better. So if you're a little annoyed right now by the news I've just dropped on you, I fully understand. But very shortly, we will see that it's nice to be able to interpret it that way. Okay. All right. I feel like I'm being a horrible salesperson on that. All right, my friends. I'd love for you to do what you can with example 1. Says graph each relation on the same plane. And I'm guessing we could all use a little more practice with the x equals y squared part. And so that's why I've chosen to use that as our parent function for example 1. Okay, so go ahead and do what you're going to do with it, and then I'll go through it with you in the next video.